In this section, we are going to discuss the data structures, which we have seen in earlier sections. First, we have the problem of finding the minimum or maximum values of 10 randomly generated numbers, which are between 0 and 100, or randomly generated numbers may correspond to people arriving with different departures from an airport. So their time of departure may be at different times. So the third person may have the earliest departure. So you might want to sort them. Let's say you have only one counter, so you ask people whether whose departure is the earliest, so you put them into queues so that they don't miss their planes. I wish they did that in airports, but they don't most of the time. So when you want to sort some collection of numbers or entities, you need to first check the current minimum with the minimum you have encountered so far with the current value. So we start the minimum variable to be the maximum value that can be encountered, and we set the maximum value variable as the minimum value that can be encountered. So when we have this number in our for loop that we generate using the range function, so we generate a random integer between 0 and 100. We check whether the current number is less than the minimum. For the first number we are generating, we have to guarantee that the minimum number is less than the initial value. So if the number is, let's say, 10 compared to 100, so the minimum becomes the number we have picked so far. So if we started the minimum as 0 initially, we would never find the current minimum. So our number is going to be more than 0 most of the time, and this check would not work. So the number is 10, let's say. It's not less than 0 because we have mistakenly set the initial value of min to 0. It would not be setting the current min to the number, and it would report a wrong minimum value which was set as 0 initially. So we have to put the maximum value as the initial value of the minimum variable, and the minimum value as the initial value of the maximum variable. In this solution, we can iterate over multiple numbers and compare them to the current minimum and current maximum, so that we can find the smallest and largest numbers that are generated by this random number generation sequence, which is executed 10 times in this solution. And as I said, this might be some other problem. You might want to find the student with the lowest GPA or the highest GPA in your class, or you might want to sort the running times of athletes, so who has run 100 meters in smallest time, shortest time, or who has run it in the longest time period. This is just for finding the min and max values. It's not sorting the numbers currently, but we are going to discuss that as well. Before them, we have these data structures, which we call a dictionary. We discussed them in earlier sections, as you would recall. So a dictionary is a key value pair storage. It doesn't store the values based on index values as in tuples or lists, but it uses the elements, the values mapped to each key. So the keys are going to be unique. You cannot have a key and multiple values corresponding to that key. You can do that if you, let's say, map, let's say we have a key of 1, and if you map a dictionary or another list, you can store the multiple values in this manner, but you cannot have the same key corresponding to another list or a dictionary or whatever. You have to have one key as the number 1 or the number 100, whatever that is. You might have keys of strings or other immutable objects. So there has to be one value corresponding to a key in a dictionary, but the value part may be a complex type which is holding multiple values. It's okay, but there can be only one entry corresponding to this key in your dictionary. So we have this bookshelves dictionary which starts with this curly braces. Okay, this is the parentheses we use for dictionaries and sets. And as the entries, I have a key, the grapes of wrath, which is stored in bookshelf A2S5. A2 might be the cabinet, S5 might be the shelf of that book. And we have another book stored in a different shelf. But as you see, the Hobbit is also stored on that shelf, B7S2, B7S2. So the shelf might hold multiple books. It's okay, but you cannot have multiple shelves corresponding to the Hobbit. So if you have something like this, B8S7, let's say, this one is going to override this one. If you allow the books to be stored at multiple shelves, you should be keeping them as lists or tuples or other dictionaries instead of individual references, B2S7, let's say. So you might have multiple copies of The Hobbit scattered on different shelves, but this line has to be unique. This entry, the key entry, has to be unique. You cannot store multiple keys in a dictionary. The last one inserted is going to override the earlier one. So when we open this and execute the dictionary example, so if I want to check which shelf the Grapes of Wrath book is, I request the bookshelf to return the corresponding value of this key. So the Grapes of Wrath corresponds to this value, A2S5, which is output on the terminal. In lists and tuples, we were providing some index values such as 10, such as 11, 100, whatever. We were providing numeric values to lists and tuples to retrieve items, but dictionaries don't work that way. They receive keys, which can be strings, numbers. Okay, if you ask for bookshelves 10, it's going to check whether there is a key set as 10 in this dictionary. If not, it's going to return something like none. I couldn't find it. And it's not going to check an index value or a positional argument for your dictionary. Okay, I think we have discussed these. You can have a mixture of entities that can be stored in your dictionary. Python does not argue about those or complain about those uh, type differences. It can store anything in a tuple list, any mixture of values, data types in both in all data containers such as dictionaries, sets, lists, and tuples. So if you ask for this numeric value to your dictionary of everything, as we have an entry corresponding to this key, it's going to retrieve the textual representation of the number 3. But this is not a positional argument. So the first entry, although it's not stored in an order as you might expect, so there's no such thing as my favorite number is stored at position 0, 3 is stored at position 1. Dictionaries don't work this way. Okay, there's no positioning in a dictionary or a set. The implementation of this dictionary structure might change from computer system to another system. So they might be storing them as linked lists. Okay, linked list is the data structure you might want to look up. Or there might be a storage algorithm of a tree structure. Okay, it might be organizing its internal data on a tree. This is another data structure you might want to look up, not for this course, but just some other advanced topics if you're interested. So the dictionary might be holding its data. Let's say book, the 3 might come before my favorite number, so it has a value of 3. And after that there might be this my favorite number key, okay, which contains the value of 8, etc. So there's no ordering constraints in dictionaries, but if you use a list, its first element is stored at index 0, its second element is stored at index 1, so this order is preserved, which is not valid for the dictionaries. In this example, we have two dictionaries, which is one of which is the runtime dictionary, and the other one is even odd dictionary. So we pick numbers from 0 to 10 and check whether they are even numbers or not. If the number is even or odd, in both cases, we append some numbers to the runtime dictionary. The runtime dictionary receives 2 times the current number if that number is an even number. And the even odd dictionary receives string representation of that number appended as string as is an even number. So the number is an even number because the even number check is true. If it's an odd number, it appends 3 times the number to the runtime dictionary and appends the number is an odd number to the even odd dictionary. So corresponding to each number, when we are appending to the dictionary, we use the current number which starts from 0. So it becomes something like this. Runtime dictionary is, for the first entry, it becomes 0. 2 times 0 becomes, which is 0. For 1, there's a comma after the first entry. For 1, it's an odd number. It's 3 times 1. For the number 2, which is the underscore, current underscore, it's going to be 4 because the number is even. And for 3, the value part is going to be 9 because it's going to multiply that value and append it to that key in this runtime dictionary. So this is how it proceeds. The similar things happens when you are populating the even odd dictionary. So as you see, 0 is an even number, 1 is an odd number, 2 is an even number, 3 is an odd number. Corresponding to 0 we have 0, corresponding to 1 we have 3, corresponding to 2 we have 4, etc. So this is how we populate the dictionary in a simple way. We might use this data for some purpose. There is an online example for drawing shapes. I think we have the reference somewhere here. Maybe at the end of the section. Okay, here's the reference to your code. If it's still valid, I don't know. So there is these shapes organized as number tuples. So when you want a square, it's going to return you this tuple. So these correspond to how many X characters you are going to display at each line. So at first line you have 0 X's. Following 10 lines, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Following 10 lines will have 10 crosses, and after that you have 0 crosses. So when you ask for a square, the program is going to return these sequence of symbols. My pen is acting weird. So there are 10 x's in this direction, 10, and there are 10 lines in this direction. So although it doesn't look like a square, but the width and the height of the shape is equal, containing equal number of x's. So there are 10 x's in this direction and 10 x's in this direction. Similarly, you can describe a triangle, so that whenever you want to draw this triangle, it's a fixed triangle, but we use a dictionary for this purpose. And if we request the number of x's on each line, on each consecutive line, we are going to receive 0, 1, 3, 5, 7, so that we can use these values to output our shape using the defined xprint function. It just multiplies x times the current value in the line. So the line width is 50 by default, by the way. So if you don't provide this value to your xprint function, if you say xprint, let's say 10, and not if you omit the line width 10, the line width argument, it's going to initiate that line width parameter as 40. You can also call it with 50 or 100. You can also provide it as a parameter, but if you skip this second parameter, it's going to initiate it using the default value. And you can simply output these results, these shapes on your console. Let's just execute it quickly. Here we have the key iterator for key in our shapes, or shapes.keys. They return the same thing. You just print the key first. It says square, triangle, diamond, or there might be another ordering when you execute it. Let's see. It starts with the square, continues with triangle. It obeys the rule, it obeys the order for the current execution, but this is not guaranteed, by the way. It might change. It doesn't guarantee that it's going to give you give the keys in the same order you inserted them, but it might preserve it for some time. When you insert something new into your dictionary, the order might change. So cross may arrive before triangle when you use this for loop. For the time being, it obeys the ordering. It adheres to rule, adheres to ordering or initial ordering of the dictionary, and it picks the shape row tuple from the shapes dictionary using the current key. The key, if the key is square, it's going to retrieve this part, the tuple containing the number of x's at each line. Okay. So this is just a fixed square. It is 10 by 10. It's a 10 by 10 shape. So it's always going to return this tuple. It's not going to be altered. But you might use other structures in your dictionary. Let's say you might insert square of square 3. So in that square 3, you might hold 3 by 3 data for your shape. Also, you might have square of 4, 14, whatever you need in your program. And after that, for each item, for each record in your square tuple, it's going to call this xprint function for 0, for 10, for 10. It's going to execute this 10 times, and it's going to execute it for 0, xprint 0, xprint 10. And this function, as you would guess, is going to add the pipe symbol, add necessary spaces, and add x's if needed. Let's say it needs 10 x's, but some spaces. So if we provide the line width as 100, it's going to calculate how many spaces are required before starting to print the x values and how many after the x values. So this is the variable. You can check and modify in your program. We have the len function, as you have already seen. It returns the number of elements in a list, in a tuple, in a set or dictionary. Let's run this example. So our list contains 7 items. 1, 2, 3, 4, 5, 6, 7. It contains double 6, but this is allowed. You can have duplicate values in a list, so it doesn't, having the name, having the word list in a variable does not imply that it's going to be a list. A list has to be initiated using a pair of square brackets. Similarly, we have the tuple example, which is defined using a pair of regular parentheses instead of square brackets, and it also allows duplicate values. So these two keep the order of elements. The first element is at position 0, second is at position 1, and so on. But in a set, although you define the 6 multiple times, the set only preserves the value 6 only once. It just ignores the duplicate value, and the length of the set becomes 6 instead of 7. Similarly, the dictionary has, as you already also see, that the order of elements is not preserved in a set. We have inserted 55 before 6, but when we try to output the set, it implicitly sorts those values, but it doesn't guarantee that your set is going to be sorted at all references. The set ordering might change at some point, so don't rely on this fact you see here. So this is a temporary ordering. It just sorts the items from smallest to largest, but at some point you might insert values to your set, and you might have some value like this, let's say 500, and after 500 you might have 155. So in runtime, your set ordering might change. You cannot say that the third element in my set output is going to be the third smallest item. There's no such ordering in a set. There's no guarantee that the set is going to provide you the items in an incremental order. Dictionary is a variation of the set. So it's just an extension to the set. For each key, you also have a value part, just separated by a colon, key, colon, value. So this is the entry for the dictionary, but the key part is this set representation. They have to be unique. So we have 5 elements corresponding to our dictionary, where we see the len function returns the number of elements in a list, in a tuple, in a set, and a dictionary. So the len function does not count the elements inside the value parts. This could have been a list or another collection which might contain 1000 items. Okay, it would still return 1 for this. It would count it as 1 because it's counting the keys, not the value part. Okay, these are all we have discussed. So the positional ordering is different than magnitudinal ordering. Positional order does not give you anything about the quantity of the elements stored in your collection. And I think we have another example. Here we have the sorting problem. Sorting is that you order the elements based on their magnitude, or based on their quantity. If you want to sort 10 randomly generated numbers in an increasing order, you have to be comparing them one against the other. So this is the solution. Let's see. We have this numbers generated and appended to our list. It's changing its size. So we have this list containing our random numbers. So we might have 99 as the first element, 7 as the second, 19 as the third, 0 as the 10th, etc. So we just picked 10 numbers. They're all they arrive at different ordering. So we need to sort these. In order to do so, we keep a temporary variable if the current value, so it starts with this range. We have the index starting from 0, going all the way up to the length of the list. So it's going to be processing 0, 1, 2, 9. So this is an index, not the values retrieved from the random number. Okay. Let's say 10 is the, 11 is the last one. So this is our list. We're going to iterate over this list, checking the second one against the first one. So this is why we start with the index plus 1. The index is 0 initially. We are going to check this one against this one. If this one is less than this one, second one is less than the first one, we are going to swap their positions. So in order to do that, we take this one out to the temp variable. Okay, this is list 0, list 0. We assign it to the temp. We replace the list 0 with the value from list, the value from list, again writing the same thing. We replace assign temp to be list of 0, and we are going to overwrite the value in list 0 with the value from list 0 plus 1, which is 1. So this is the secondary index, and we repeat this process for all values following the secondary index. So we first swap these values. Now these two are changing locations. Becomes like this: 99, 7, 11, and then our secondary index moves on. We check 7 against 10, and then we swap these two values: 7, 99, 10, and now we check with 11. So our index is fixed. At this point, we know that after, let's say we have 15, 17, etc., we have no smaller items than 7 in our current list of 10 items. We check this position, the value in this position, against all other values in our list. So we swap the values as long as there are smaller numbers, and then our index is incremented to 1. We know that the smallest number is location 0. At this point, we check 99 against 10. So this is index 1. 1 plus 1 is 2. This is the secondary index. We keep changing their locations at the second position in our list, as long as there are smaller numbers. So we now know that the second smallest number is at position 2. So this algorithm is the basic exhaustive search algorithm for sorting numbers in a list. There are other sorting algorithms, efficient sorting algorithms, depending on your input, which might complete this process in a shorter time and by using less resources such as memory or CPU. For 10 numbers, it's okay to use a primitive solution like this. But if you are dealing with number sets of millions of entries, that you might not have the resources or sufficient time, because it's going to increase your response time to the user. You might have to use more efficient sorting algorithms, which you might find online, such as bubble sort, uh, bucket sort, etc. There are many of them. Depending on your problem and depending on your data set, not each algorithm is going to perform better at all conditions. So if your list is partially sorted, you might want to use a specific sorting algorithm. If there's another case that fits the sorting, there are multiple tens, if not hundreds of sorting algorithms. You might want to utilize the correct algorithm for your correct problem. This doesn't mean that you have to use the same sorting algorithm throughout your program. You might find one of them handy at some part of your code and the other sorting algorithm in another part. You can also try to find the index of minimum and maximum numbers in your list. That's also important. You're going to simply modify this and check whether there you have encountered the minimum number currently. We have already found them, but doing them in the same loop is more efficient. So processing this list once gives you a complexity of n. N might be 1 million. Okay, 100 million. If you repeat this process once again, you are going to increase another, introduce another 1 million processing to your CPU cycles. So if you're already processing them here, you can also check the minimum index and maximum index values in the same loop, eliminating the need for reiterating your lists over and over. You can also have lists of lists, okay, which you might call multi-dimensional lists. A multi-dimensional list is simply a list containing other lists as its individual entries. Okay. So when you refer to timetable 1, you check this one out, the second entry, and from that second entry you simply want to retrieve the second item. So this is 0, this is 1, this is the second positional index. If you refer to your timetable, you will have all this printed out. If you refer to your timetable access 1, you're going to get this line, this sublist, this entry of your original list. And from that list, you access the timetable, first entry in your timetable, and the second entry in your first entry, which is going to Math 101. This can be used as a multi-dimensional list, and you can simply just switch to code and run this example. It first prints the entire list. From that list, it prints the first entry, and then from that first entry, it prints the second entry. You can access any item in your two-dimensional list. You can have three-dimensional lists, four-dimensional lists. There's no limitation in accessing all those or designing your problem in such a way. Just you should just be careful which index corresponds to which item in your list. So we have this three-dimensional list here. List 0 corresponds to this two-dimensional list at the first line. And from that list, we retrieve another list. And from that one, we have this string, item at 000, just a string for you. It's going to output the results accordingly. And let's see. These are the other examples. You should be careful about the values contained as lists and the access operators. So these are the access operators. They are not lists. They are used for referring to an item in a list. Just change these numbers and see what it outputs. So there's no relation between the values contained in these lists and the index values. It just refers to those items. So it's which one it refers to? Dimensional list 2. This is the second, and the first from that one is 7. So this is going to return 7. These are for addressing purposes. They are not the lists. But when you are defining your list, you have to use the square brackets. If this wasn't a list, it could be a tuple. Okay, you could have defined them as tuples as well. This would still work the same way, etc. Okay, you would still have to refer to this index using the square brackets. So these square brackets, when used after just append it to the list itself or the dictionary itself, or the tuple itself. When you append it to a list or tuple, it is an access operator. It doesn't define a list. It just goes to the correct element you are trying to access. Okay, I think there's another, this timetable example. You can simply print out the days and each course in each day using this example here. Do we have the switch to code button? I think we don't. Anyway, you can just copy this and paste it to your example part here and execute it and see the result yourself.